All right, good afternoon, everyone. Welcome to Midwest Bridge. It's my pleasure to be presenting to you. I know we're kind of backed up to a break here, so I'll try to get through it. There are a lot of videos, so some eye candy. I probably won't let them all play through all the way, but anyway, I'm going to be talking about digitized workflow for bridge inspection today. My name is Marc Parker. I'm with Collins Engineers out of the St. Paul office. And I will kind of start with discussing what the inspection workflow is, and then I'll walk through a case study of the Robert Street Bridge project that we've done with MnDOT in downtown St. Paul. That's what you see there. So the concept of a digital twin, many of you probably know what it is. I know Todd kind of brought it up. Josh is a pilot. He's kind of working with South Dakota to do that. And I think we all know what it is, but in case you don't, it's basically a digital rendering of a real-life asset. So sometimes they're a point cloud, sometimes it's a mesh, but in any case, it's a geometrically accurate rendering that can be viewed on a digital platform, so computer, portal, whatever it may be. Maybe a little less of you have actually interacted with them, navigated them, used them for bridge or asset models. Really what we're seeing here is the ease of introduction to the digital twin is using it for collaboration, communicating, pulling it up during project review meetings and team meetings to kind of navigate around a bridge. If you have a question about a specific area, you can kind of navigate and the entire team will follow, be able to kind of see it, visualize it. You don't have to dig through photos to find it. So that's kind of where we're starting with some of these. We also are able to see this from anywhere. So, in a kind of remote time, a lot of people work remote, not everyone's able to get to site. You can kind of share these digital platforms with your entire project team, whether it's local or not, and everybody can view it either on their own or together, collaborative, whatever it may be. So even less of you have probably actually created these models and used them for inspection or data entry, things like that. That's kind of what I'm going to talk about today, is actually creating the model and then populating it with inspection, annotations, data, all that stuff. So real quick to just talk on creating the digital twins. This is the first step. Obviously, you got to capture the data. There are several different methods. You can do photogrammetry using a camera. You can do LiDAR. What we've found is most efficient is using a camera to capture photographs and then using a photogrammetry post-processing software. The LiDAR imaging is a little bit more expensive. Requires a little bit more post-processing on our end. So really what we've been digging into is the photogrammetry aspect. I think a lot of people probably associate that with drones. I think that is a good chunk of where the imagery comes from, but we've had really good success with all sorts of imaging platforms. So a lot of us use our smartphones in the field to capture localized areas, and then we're able to render that later when we get back in the office, or even using some apps on your phone. We've used things like GoPros to record video and then cut frames from that and made models. So there are many different options that are kind of outside of the realm of drones. So it's not just drones that kind of get you this imagery. And then lastly, there are quite a few of, industry advancements in kind of the digital modeling that are coming to, accessories, I guess I'll call them, to aid the modeling and create a more reliable product. QR codes, most photogrammetry products now will auto-identify QR codes and create automatic tie points to create the model. So we've been using those on most of our inspections, and it just creates a much more reliable model in the end. And then ground control points, like what you see here, provides a survey control point target for input into your model and processing. So I guess there's many benefits of utilizing the digital twin, and I'm only going to go over three really. The first one is accessibility. The second one's accuracy and precision, and the third one is data management. So for accessibility, I kind of mentioned it before, but being able to kind of share the site with anybody, anywhere, anytime is a huge benefit to any bridge owner. A lot of the times you wouldn't necessarily be able to get in a certain perspective, whether there's only so many people allowed in a snooper, you just don't have the time, your staff isn't physically able to get on site. You're able to share these digital twins and view them from a bird's eye perspective or any other perspective. You'll see, I'll mention it in a little bit, but the model rendering is not always the best, I'll say, quality. Sometimes you have holes and girders and things like that. However, it's really important to just remember that this is derived from tens of thousands of photos. So you can navigate to one spot in this bridge of interest, click on it, and it'll pull up every single high-resolution photo of that area. So, we are still working on the quality of our models, and it's progressing, a lot over the last 5 years. But there is a whole catalog of digital photos that kind of backs up these models. So that's, as far as accessibility, we're seeing a huge benefit in working with your team, collaboration, things like that. As far as precision and accuracy, we're getting more advanced in our ability to model things. This is just an example of a steel section that we modeled to essentially measure steel section loss. Now, this is obviously on a much smaller micro scale, if you will, a little bit different than a global bridge inspection. But the point is that we're able to capture 3D data. So whether it's an entire bridge or a small steel section like this, you're gathering so much more data than you have in the past. You're able to, within your model, have a location, a type of defect, a size of defect, and you don't have to necessarily rely on traditional methods like sketches or maybe textual notes, things like that. It also serves as a really great platform for revisiting, verifying, and QC/QA of different, whether it's an inspection report or revisiting a site. So if you have an inspection report maybe that says, this crack was this long and this wide, you can revisit your actual model and determine, measure it in real length in the model and say, was it that long? I know there's some people who are doing a digital quality assurance checks of their bridge inspections. So once you have a model, you can kind of have another set of eyes look at it without actually having to mobilize in the field. So that's another situation where the quality and the precision of what we're seeing is, pretty much it's been proving very valuable. And then, as I mentioned, we're not necessarily to the level yet where we can measure steel section loss in the same capacity we would with the D meter or something like that. However, we are able to get close, right? And we're able to start using it with the emerging technology, the size of photo sensors, LiDAR, things like that. Within the next, it's only a matter of time before you can measure crack widths and steel section loss and things like that. So the last thing, or benefit, I guess, is just data management. Within complex structures, you might have thousands of defects that you are going to have to record. A lot of the times with traditional inspections, those defects might get generalized. They might get, more typical annotation. When we're doing, or when we're using a digital twin to actually do the inspection, what we're finding is that when you observe a defect, you're entering it as a defect in the model, and it doesn't get lost in, a summary or a generalized comment. It's actually a single defect, a single line item within the inspection. So as far as the granularity of what you have, all your data is stored. There's no loss in data. There's no loss in sketches or anything like that. So that's the data management. That's kind of what the digital workflow that we're seeing the benefits from here. So Robert Street Bridge is a complex structure in downtown St. Paul. We're working with MnDOT to do a special structural inspection on this. It was a complex or in-depth inspection to kind of identify all concrete defects. It did require us to have a hands-on inspection of all concrete surfaces. So we determined that this was a good option for trying to use this digital workflow, and it did provide to be quite advantageous for us. So the workflow is basically you're going to go out, you're going to capture the data. We did use a drone. The drone took about 3 days to collect the data, and then we did about 1 day before that to set QR codes and ground control points. So not a whole lot of time and effort. It was only a 2-person team out there that had to collect that data. The next step was the creation of the digital twin. It took about a month to do, but that was mostly computer rendering time. I think it was maybe 30, 40 hours of an actual engineer going in and changing inputs and rerunning it. So a lot of processing time, not a whole lot of actual engineering time. There is a lag, you do have to allow for that processing time, and depending on the complexity and what your data is and what your tie points and things are, it can vary greatly. Then we did an office pre-inspection. The time frame for this was a little bit crunched, so we wish we would have had a little bit more time to review in the office. But what it is basically we had our engineers navigate through the model on their desktop screens and start populating defects. So anywhere there was a spall, they were able to measure it, quantify it, add notes, put a pin, and then basically continue to navigate. And then by the time we're ready to go out in the field, all those are already pre-populated in the model. So that led to a field inspection. It's really important to note that we're not replacing any type of physical inspection here. It's really just a matter of efficiency and a matter of better quality data. And then we're going to provide this as a deliverable to the load rating engineers who are going to use that in their complex model, and then eventually construction and final rehabilitation plans. So to kind of dig into each of those, the digital model consisted of over 100,000 photos, several terabytes of images, over 100 hours of computer processing. We broke it into several segments just for the sake of rendering. We took each span basically and ran that through the machine, and at the end you're able to take all the blocks and kind of merge them together. However, as some of the folks from MnDOT and others that might have seen it, it's pretty tedious if you have like all the blocks turned on, you're trying to navigate the whole bridge. So data is a, hurdle that we need to overcome. I think the machines can only progress so fast. We're able to share this with the team in real time. So before we even went out for all the inspection planning, when we're talking with the inspection team and the project team, we can pull this up real time, navigate through different things. If they have questions on, hey, can you go to the Pier 4 second span roll? I think that there's something there. We can look at it real time on a meeting with the team. We used a Skydio 2 Plus to collect the data. Almost all the data was captured using autonomous flight. This is a function of the Skydio 2 Pluses. They use both a visual visual system to navigate where they're at, and then also some GPS enabled. But basically what you're seeing is the AI of the drone actually picking up the different surfaces. It does a preliminary flight, figures out what the surfaces are, and then it'll just keep scanning until essentially it knows it's reliably caught all the surfaces of whatever you're trying to model. There were some areas within those tight, where the barrel arch, between the barrel arch and the deck, that it did not go in, but it did go in the outside ones, which was nice. Lighting did prove to be a little bit of an issue. But basically what you see here is it darkens in color as it gets more coverage. An issue that we've seen in the past is that when you go out in the field and you collect the data, there's not a very reliable way to know that you've got the coverage you need to come back to the office and make a model. Sometimes you get back to the office, you run the model, it takes a couple days, and then all of a sudden you realize you have a big hole somewhere in a deck or something. So, Skydio specifically has come a very long way in kind of producing something that's much more reliable in the field. We did use approximately 100 QR codes throughout the bridge and set about 30 survey ground control points that the model automatically detected when it was being produced. So the next step was the desktop review. This is an example of kind of what they would find in the desktop. They would do a visual inspection through navigating, anything that's visually or that you could see without actually putting hands on, spalls, exposed reinforcement, wide cracks, things like that. our engineers were able to go in and create a defect note. We were able to basically create our own form, a tailored form for our inspection that contained whatever information we wanted. So it has a defect ID, a location, an element, a condition state, additional defect data. For the load rating, it was really important that they know if there was debonding of the reinforcement and how long that was. So we had a section where we could enter that into the actual form. Now all this data is going to be field reviewed, but we're populating it before we even go out. So that's really where the efficiency comes, is that you're not out in the field having to record all this information, you're not having to like go and do the whole inspection in the field. You can do a lot of these notes prior. We used a tag color system, which the Bentley product we were using kind of set forth, but there's different color tags as the defects go through different quality checks or checks throughout the process. So purple was a office identified or desktop review defect, and then when you go in the field, you review that and you change it to field verified, and then when you go back in the office, you review that and you changed it to approved by engineer, and then there's different steps. So the color coding of the defects was also really helpful in our review because there were just so many defects. We were able to pre-populate about 500 defects in the model prior to even going out in the field. We use the photographs a lot to help or aid in our identification of these defects. As I mentioned, the model, while the quality is very good in our eyes, there are parts that maybe are blurry or not super clear. You again realize that there's a huge inventory of photos, high resolution photos. That's what you see on the right, where you can click on an area that might be suspect. It'll pull up a whole list of photos that you can navigate around and get different perspectives of it. So you are able to kind of get a much better view than just what the model shows. So if you are ever navigating a digital twin and there are holes in girders or decks or things, just realize that there's likely a whole library of photos that follows that you can use to also make judgment calls on defects. Let's see here. So following that, we did our field inspection. We were able to utilize the digital twin in the field, so we actually had tablets with the digital twin pulled up. It was cellular connected, so it was real time. Our inspectors basically walked and used the snooper throughout the bridge, went to defect. We had to hammer sound all surfaces, so there were quite a few defects that were added because there were delamination and they wouldn't have necessarily been able to be seen from the initial model. We also had, once you had a delamination, you might have to expand the area of the defect, change different attributes that we have in there, condition states. So there was quite a bit of modifying in the field. However, for the most part, the defect was identified, it was labeled, it was located, the severity was mostly correct. But out of those 500 that we pre-populated, we ended up with about 1,300 final defects. So the granularity of the inspection was, not lost at all throughout the procedure, and that's really where that data management comes in. We created a digital, or our deliverable for this is still in the final works, but basically there's 3 things that we're providing. We have the model itself, which has a geolocated defect with all the different information. We created that form, and there's an export that every single defect can export a PDF printout of what the form is, what the data related to that defect is, and the most optimized photo of that defect. And then the third thing is an Excel or a spreadsheet printout that's basically a line item with every single input that we put, or every single input we identified has a column, and then every defect has a row. So we are able to turn that over to the load rating engineers, and they can filter it however they want. If they're interested in only the spandrel arch ribs, they can filter out just those defects. And if they're only interested in section loss with debonded rebar, they can filter that. And it'll take that 1,300 defects that we recorded down to maybe 40. So, I think we all enjoy the perks of spreadsheets, and there is a bit of learning curve to navigating the model, and there's definitely a little bit of lagging when you're actually trying to view the model. So we're trying to really use different platforms, different methods to make it the most efficient process, whether you're looking at it for load rating, or if we're going to create a inspection entry into their data asset management system, we can kind of consolidate all that information. That's not, you don't have to access the actual the digital model. So I guess a little bit of where this is going. The AI is really kind of the next step. I'm sure everybody is aware that they are already doing AI crack identification. It's only going to get better. This is the Robert Street Bridge we ran. There's really no extra time that's involved for it to produce this. It's just another rendering that basically the computer has to run. But this is going to serve the Office desktop review to be much more efficient. You can kind of go through and it'll give you a list of all these cracks. It'll say, is this a crack? And basically you're going to say, yes, positive, that's a crack. Possibly that's a crack, or maybe it's a false positive, that's not a crack, it's a joint or something. And that way it kind of gives you a little bit more focus when you're in these models. You don't get lost searching for things in the detail. Obviously it's not perfect. You're not going to be able to identify hairline cracks in photogrammetry. It's just not there at the moment. But we are really excited to see kind of where this is potentially going, because as I said, you can pretty much quantify the amount of cracks in this with little to no extra engineering input once you have the actual model created. And then that's not just for cracks. They are starting to do things like spalls, exposed reinforcement, you name it. As long as it's visual, as long as you can visually see it, then it's something that is potential for AI to pick up in the rendering. So, digital workflow benefits, just to kind of recap, the collected data is so much more granular than what we traditionally would have. As I said, we had 1,300 individual defect line items. I don't think we would have been able to get to that level of granularity had we not used or implemented this system. A lot of times traditional, you get, as I said, typicals or general notes. They're not all necessarily CS3, CS4 cracks, but you do have a full list of CS2 cracks that might over time become CS3 cracks. And now having that baseline moving forward, you're able to take this data and compare it to your next inspection. So you have a crack, it's a CS2, you know where it was, you know the length, you can go revisit it, measure the crack, did it grow, is it wider, is it progressing, things like that. So the data is much more granular, much more complete. Safety, obviously we all know of workplace injuries or traffic control, on-site injuries. We are reducing the traffic control time and the time for the inspectors in the field. For the Robert Street specific, it wasn't significantly reduced because we had to still hands-on everything, but it was, I think we bought ourselves probably an extra 4 days that we didn't have to be out there doing hammer sounding. For more routine situations, if you were just doing a routine physical tactile inspection, you could fly the drone up to the bearings and see certain areas. You could model if you model the bridge, you can enter defects in without necessarily needing a snooper maybe, or needing traffic control. So if it's more of a routine inspection, you definitely have the ability to save more time and make a safer environment for both the traveling public and the inspectors. The data is easily stored. I think we are all getting to the point where a terabyte of data is not anything unruly, but there is still quite a bit of management that we need to do in figuring out how to transfer this to the client, who owns the data, who's accessing the data, but it's out there, and it's able for anybody that wants and has the ability to view. The collaboration is going to be, as we said, the key to kind of utilizing these and introducing it to the field of, bridge inspection, basically. And as we finish the designs, the model doesn't change. It's a point-in-time rendering. So as you finish, rehabilitation designs, things like that, you can use this as a tool to have others visit, whether it's a contractor bidding on the project. They all have the same access to a portal. They can answer some of their own questions as far as clearances and construction staging. The design team can use it for the life of the structure. So yeah, it really just comes down to a matter of collaboration and data that you're capturing. So that's really all I have. Big thanks to MnDOT for their continued support of digital twins and implementation of this technology. And then also, thanks to Bentley, Skydio, and Propeller for some of the products that we've been using. And if anybody has questions, my email's out there. I'll be out at the booth for.
We got a minute or two here, so one or two.
Thanks, Drew.
Mark, thank you very much for the great presentation. I've got two questions, actually. One is, what we've been seeing is, especially when you are using, for example, drones or a Skydio drone for imaging of the underside, when the drone takes pictures, it doesn't go in the areas in between the girders. So when you do photogrammetry, the area between the girders and pretty much under the bridge looks very flat, as if like there is no space, for example, in between the girders. Did you guys find any kind of workaround for it, or for now it is because, as you mentioned, we are using like the model as a way to find, for example, different things, or find like the exact picture that, for example, put that part of the model together, because that is the use case, we are not really concerned about that. And my second question, you kind of mentioned it, but if you can go a little bit more in depth into it, is when it comes to transferring of the data and some of the results to the agencies, most of the time we see that agencies have pretty much very secure or closed computer systems. So even when certain applications are needed to open like a very large file, sometimes agencies wouldn't be able to do that. How did you folks approach that problem as well? Thank you.
Sure. So the first question, it's all a matter of diminishing returns, I suppose, and how much detail you want to put into it. We did go inside those barrel arches and image the interior with lights and cameras, but we didn't do it for all of them just because there wasn't, the return that we got from it necessarily wasn't great. So for all the open spandrel arches, which let's see here. Examples. So like these, I mean, the drone was able to capture all surfaces of everything that was not within 4 feet of something. And we got good coverage on everything. Concrete structures are much better coverage than steel structures. But yeah, I think we got all the coverage that we needed for the purpose of the inspection. And the second question, as far as data, it's a work in progress. There's different avenues that people can go. I think a lot of the photogrammetry engines and providers are coming up with their own systems that might integrate into things like Open Roads or Open Bridge. I don't have a great answer as to how it's going to happen, but I know it will happen. It's inevitable. It's just a matter of who's going to own the data and who's going to use it.